All right. So thank you so much for the introduction. And I'm very grateful to the organizers for the opportunity to present our recent research. And so I'll be talking about the ways for probing the complexity of particular instances of hard problems for evaluating existing and new Ising machines. And so to say up front, our mission is not only to evaluate the existing computer machines, but also to understand the essential ingredients and principles that can help us build the new ones. I also understand, as you mentioned, that that's the last talk of the last session, and that's why I try to make it easy to follow. And I will be giving the story from the perspective of a scientist who has access to some physical system, physical platform, where networks of some physical elements can be realized and the interactions between the elements can be controlled to some degree. And then the question is, can we solve any optimization problems with this physical system or not? So doing some quick research, one can quickly realize that there are lots of hard optimization problems, from knapsack problem to chip design to traveling salesman problem and protein folding, which can be represented as graphs, unweighted and weighted, sparse or dense. And in these graphs, spin Hamiltonians can be optimized, and the ground states of the spin Hamiltonians eventually may correspond to the optimal states of these hard optimization problems. And we've got quite a few choices of spin Hamiltonians, which are Ising, discrete model X, Y, pods, and even not only pairwise interactions can be considered, and we can consider k-local Hamiltonians. So in my talk, I'll be talking about the Ising spin Hamiltonian. So the Ising spin Hamiltonian is shown here on top. Basically, it's a quadratic unconstrained binary optimization problem with coupling interactions J between the elements. And when it comes to building a new simulator for solving, in this case, Ising model, so or any other spin Hamiltonian, so usually you have some limitations for the physical platform, which are commonly the ability only to engineer at the beginning small size problems, commonly a few tens of elements, maybe a few hundreds if you're lucky. It's also common that we have limited connectivity. Let's say like 3 or 4 or 5 connections per each element may be possible to realize with the current setup. And it's also common that coupling strengths between the elements, they cannot be controlled to an arbitrary degree, and their strength cannot be changed between some ratio. So that's why this leads us to the common choice of the graphs on which to try the Ising model, to solve the Ising model on the physical platform, which is the unweighted free regular graphs. The unweighted means that we have only couplings of the same amplitude and the same sign, and the free regular means that we have exactly 3 neighbors for each element in the network. So these problems are proven to be NP-hard, which is good. If we solve them, then it could be generalized. So then our ability to solve hard problems can be generalized to any other hard problems. And this formulation of the Ising problem on such graphs is equivalent to the so well-known maximum cut problem. So okay, we've settled on unweighted free regular MaxCut problems, but still there are lots of choices of graphs which we can consider. The question is, are all of these graphs are equally hard for Ising optimization or not? So, because with respect to the complexity theory, we can have problems which can be solved in polynomial time and belong to P class. We can have problems which belong to NP class, non-deterministic polynomial time, and we can have the hardest problems here on the right side. And the thing is that even if your problem is proven to be NP-hard, it doesn't mean that any instance that is generated from this class of problems will be actually hard to solve. And so it turned out that a particular type of graphs within this free regular MaxCut problems is popular, which is Mobius ladders. And the two views of these graphs are shown here. So basically, it's the network which is placed on the topology of Mobius ladders with one twist here in the middle. We have 3 neighbors, exactly 3 neighbors per each element in the network. And on the right side, you can see the circular graph, just another representation. So the good news here is that the ground state for the Ising Hamiltonian of such graphs, it's well known, and you will have only two frustrated edges for the ground state. So this is good, so you don't need to use any sophisticated methods for checking the solution that you'll fortunately get with your physical system. And the choice of Mobius sliders, it's not a random choice. So if you check the literature, so it turned out that these graphs were very popular over the last few years. They were first introduced in a great pioneering work in 2016 in optical parametric oscillators, and then were used for the last few years in many other physical systems, and optoelectronic oscillators were introduced last year in 2019, and this year many more works have used them as well. The size of the problems that can be tackled with this various physical systems, so it was also increasing over the years, so from 100 in 2016 to 800 in 2020. And the question is, so what is the complexity of these problems? And to answer this question, so if we claim that these problems are simple to solve, the only thing that we need to show is that there exists at least one algorithm that can solve them actually in polynomial time. And after a few trials, lucky for us, so we found this algorithm, so which turned out to be the famous Hopfield-Tank algorithm. It was introduced in 80s and by Hopfield-Tank in the context of associative memory. And the equation is shown here. So the amplitude of the network elements is varied with, oops, I bet. The amplitudes of the network elements X is varied in time with respect to the right-hand side. So we have linear losses, X over tau, we have the coupling term, and we also have some gain. And here V can represent the spins, and G is just some nonlinear function, activation function. So applying this algorithm to the Mobius sliders leads us to the following. The number of time iterations in the Hopfield-Tank algorithm, it scales polynomially, in fact quadratically, with the size of the Mobius slider. And here on the graph, you can see that the probability to find the ground state, which is shown in 50% cases, is shown in blue, and in 99% cases, it's shown in green. So you can see that it scales linearly in log-log plot, so basically, which gives us quadratic dependence. And what it means for us is that since each time iteration of the Hopfield-Tank algorithm, it takes linear time. It has linear complexity because it is governed by the sparse mathematic product. And since the number of time iterations scales quadratically, so the overall complexity of optimizing the Ising model on the Mobius sliders scales cubically. And so this problem cannot be regarded as the hard one to solve. And moreover, so if we take a look at what happens over time in our algorithm, so here we show what happens to the spin amplitudes in the Hopfield-Tank algorithm for 1000 size network, we will see what is shown here on top, that in the end of the time evolution, the amplitudes of the spins, so the ratio of the maximum amplitude to the minimum amplitude absolute values, it's actually 900. So our spins are not even binarized, which means that we're actually not solving as a model at all, and we're doing just something else. And to understand what we are doing, so we looked at the energy levels, which are shown here at the bottom. So GS proximity stands for ground state proximity, and 100% means that we've reached the ground state. So what we found out that the whole low energy spectra corresponds to the eigenvectors of the largest eigenvalues of the coupling matrix. And the ground state in particular corresponds to the projected eigenvector of the largest eigenvalue, which means that and this is actually well within the behavior of the Hopfield-Tank algorithm, which was established in the 80s and 90s. So what it does is that it leads your network elements in the direction of the largest eigenvalue, largest eigenvector corresponding to the eigenvector corresponding to the largest eigenvalue. So what it means for us is that we can make two conclusions from here. That first of all, that the Ising model in Mobius sliders, it can be solved in polynomial time, and so the ability of a physical system to solve hard problems cannot be claimed if only such problems considered for solving, for optimization. And the second thing is that even the ability to optimize Ising model at all cannot be claimed, because as we've seen for Hopfield-Tank algorithm, so it doesn't solve the Ising model at all, while still finds the global minimum of such graphs. So then the question is, okay, so the graphs that we used over the last few years, they may not be as suitable for demonstrating great optimization capabilities of a particular physical system. And so what should we consider then? Well, since the Mobius sliders were already in use for a while, so what we can do, we can consider rewiring of these graphs. And it turned out that rewiring only 2 edges is actually enough so that we break this dependence of the ground state correspondence to the largest eigenvector of the largest eigenvalue of the coupling matrix. The next question that can be asked, but is it enough? Is it enough to consider only one rewiring of 2 edges, or should we consider more, or what would be the percentage of rewired edges that we should consider so that the problem can be claimed to be a hard one? So what we've done is that we've studied this, and so to study this dependence, we cannot use anymore the Hopfield-Tank algorithm because it already struggles as soon as we do just one rewiring. And so we need to consider some other methods. And here we decided to consider the exact commercial solver, which is Groby. And we've studied how the time to solve the problems exactly changes over the percentage of the rewired edges. So here on the left, you can see we start with the Mobius sliders, which you can solve in some like milliseconds, sometimes in just a bit over 100 millisecond scale. And then we rewire edges more and more. And then you see that for like 60% of rewired edges, the complexity already, or 40 to 60% of rewired edges, the complexity already is equivalent to that of 3 regular graphs. So, and we've checked it for a few problem sizes. So this does not yet mean a lot for us because we don't know how representative these results are. And to get the idea of how it can be generalized to other methods, to understand if other methods, other algorithms can show the similar behavior. So what we've done, we've considered 2 more algorithms, which are arguably the current state of the art. So we've considered parallel tempering algorithm and chaotic amplitude control. And we've seen quite similar behavior that the polynomial simple Mobius slider graphs, they're simple to solve, they're easy to optimize, while the rewired ones are more complicated. The main difference here, which is actually very good for us, is that the number of rewired edges now has to be much smaller, and it doesn't have to be around 40 to 60%. And now only a few percent of rewired edges is enough to say that these Mobius sliders with only 5% rewired edges its complexity is equivalent to that of the random unweighted free regular problem. And so this makes rewired Mobius sliders actually favorable for consideration once you have a physical system and you want to evaluate its optimization abilities in solving hard problems. So with that, I thank you for your attention. More details can be found in our recent paper, not only about free regular graphs, which I have a chance to talk about here, but also about k-regular graphs and other spin glass models. So please follow if you're curious. And so this work was done by me and my supervisor, Natalia Belov, to whom I'm very, very grateful for supporting me during my whole PhD. So thank you so much for your attention.
Well, thank you very much for the talk. And the work is now open for questions. We already have one raised hand, so please, Alexander.
Yes, sure. Thank you, Kirill, for the very nice talk. I have a question about the metrics. So you see that energy converges to the ground state energy, yeah, when you simulate the system. And this is one indication you are coming close to ground state. But to get the solution for NP-hard problem, you also want to actually get the bits right, yes? So you want to check that this is indeed solution. And I've seen personally in my experience where you do imaginary time evolution, you reach the energy precision, which is extremely high, and then probability to get the right solution is very modest. So what may happen is actually you need to check the Hamming distance for this problem.
So thank you so much for the question. So, and When I'm talking about this, can you see the graph? Yeah, you can still see it?
Yeah, I can.
Yeah, ground state proximity, okay. So when I'm talking about ground state proximity of 100%, so I'm not only talking about the energy, but also about Hamming distance as well. So here, that ground state, it corresponds exactly with Hamming distance 0 to the ground state solution. So here, all the spins that can be found by the Hopfield-Tank algorithm they will correspond to the projected eigenvector, and this projected eigenvector will give you the exact ground state spin configuration of the ground state. Yeah. And
if you change a bit, you rewire the Hamiltonian.
Yeah.
Do you observe that the degeneracy of your ground state changes? Because typically, if you have degenerate ground state, it's easy to solve. If it's a single state out of like 2 to the power of n, it's difficult to solve.
So the degeneracy can definitely change. I'm not sure exactly that would be something that will cause the difficulty here. But what happens is that as soon as you break the fact that the projected eigenvector of the largest eigenvalue, it gives you the ground state spin configuration. So, and with these two rewirings here, which are shown here, so it can be done. So as soon as this thing happens, with canonical form of Hopfield-Tank algorithm, you cannot find the ground state. So even if you consider like, so I've tried to use like machine learning optimization techniques for finding all different sets of parameters to optimize it. So it's likely impossible. So what you need to do, you need to do other methods, yeah. So, and the complexity increasing is, so to answer exactly your question, the complexity increases not only because the degeneracy of the state changes. So it's not really because of that, but because of the fact that you are breaking this eigenvector correspondence to the ground state solution.
Okay, I see. But if you were to use the same method like simulated annealing, would you see the transition in the runtime? Okay, thank you.
So if we actually to comment on the last one, so if you use simulated annealing, so you will likely, well, you will definitely see the similar behaviors. That so these two methods, they can be considered as actually parallel tempering. Parallel tempering is commonly compared to simulated annealing. Sometimes quite often it shows a better performance, but the simulated annealing will demonstrate a very similar performance. So if you optimize your parameters for each percentage of rewired edges, then you'll see that it's possible to solve much faster the problems which are like polynomial simple, which are Mobius ladders. And as soon as you rewire more and more edges, you'll see how the complexity, so the metric which is here, time to solution metric. So it's not just the success probability, but it's multiplied by the time at which each iteration takes, how much time it does take. So you'll see immediately the time to solution, it increases as well. Yeah. So, and that's the whole thing why we decided to consider a few algorithms to show that it can be generalized. So it's not like we have only one algorithm that somehow can solve this in polynomial time, Hopfield-Tank. No, we can show that Groby solver here, it can show it much faster than rewired graphs with 40–60%. But the exact percentage to which you need to rewire the graphs, so it's method dependent. And that's what we've seen for other two methods.
I see, thank you. And it's not sharp phase transition, it's just gradual increase, yeah?
Well, usually it's not sharp, yeah, but yeah, it's not sharp. So you need to do a few number of swaps of exchanges of edges so that you can see this transition, yeah.
Thank you.
Well, yes, well, thank you very much for this interesting discussion. Let's thank the speaker again.